Okay, so I'm going to start chapter 4, which is on least squares. And so we're going to take a look at the data fitting problem again that we looked at in chapter 3. However, we're going to change how we are going to fit data. Okay, so previously in chapter 3, we did polynomial interpolation, okay, with under certain conditions. We used evenly spaced nodes, we used Chebyshev nodes, we talked about cubic splines. Now, all of these interpolants that interpolated our data fit the data exactly at the nodes. In chapter 4, we are going to relax that condition, okay, and develop a different idea as far as how to fit the data. Okay, so the main thing is that we are not going to exactly fit the data at the nodes. Okay, and so the way to do this is through a concept called least squares and by using the normal, what are called the normal equations. Okay, so to get this started, consider the system of equations that looks like the following: x1 plus x2 equals 2, x1 minus x2 equals 1, x1 plus x2 equals 3. Okay, so hopefully it is obvious that this system is a system that is inconsistent. That is, there's no solution. If you look at equation 1 and look at equation 3, there's no way that x1 and then x2 could satisfy both equations 1 and 3. Okay, so this is certainly a problem that has no solution. Remember from linear algebra that for any linear system, we have 3 scenarios: no solution, exactly one solution, or infinitely many. Okay. All right, so since we don't have an exact solution, what can we do? Well, we can find a solution that is, or find an, so let me put this in writing. We want to find an x hat that's equal to x1, x2 that is closest to being a solution. And I'm going to put closest in quotes because what do we mean by closest? Well, what we mean by closest is that it's going to be closest in the sense of least squares. Now, for this lecture, I'm going to not get into the theory too much. I'm basically just going to present these normal equations that are used to solve a problem like this and go through some problems. The theory I will wait for lecture. So here we're going to find, like I said, we're going to find an x hat that is closest to a solution, I'll say in the sense of least squares. And I will clarify what this means, as I said, in lecture. Okay, so before I present the normal equations, I want to just discuss some details from linear algebra. And so we're just going to discuss some linear algebra. And I'm going to define the transpose of a matrix A. And so the transpose of matrix A, and so we're going to provide it, and this is denoted A with a superscript T that looks like an exponent. So basically, if A is an m by n matrix, AT is an n by m matrix, where the rows of A are columns of A transpose. And we could also say that where the columns of A are now the rows of A transpose. And there are a couple of properties of transposes. One, that if we take the transpose of a sum, we get a sum of transposes. And if we take the transpose of a product, so we have a product of matrices A times B, and we want to take the transpose of that, it's equal to a product of transposes, but in reverse order. I'm not going to prove these. These are just, I'm going to give these to you. So these are properties of transposes. I'm also going to talk about the dot product. And so the dot product, which, just to give you the notation we're going to use, usually you might see the notation this way, U dotted with V. Our book uses the following notation, U transpose and then times V. And so this equals, of course we have to have vectors that are of the same length or have the same number of entries. So if U is a row vector with entries U1, U2, dot, 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 U sub M, and V is a column vector with entries V1 through Vm, the dot product is a scalar quantity that equals U1 times V1 plus dot, 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 all the way to the end, U sub M, V sub M.